Flying using propellers here on Earth is relatively easy due to our thick atmosphere, but NASA are embarking on a daring mission to fly a helicopter on Mars. And to find out just how difficult this is, we're going to dive into the numbers and see how it's possible. And joining me is Chief Pilot of Ingenuity. Let's get started. Joining me today is somebody from NASA's JPL. He is the Flight Control and Aerodynamic Lead, as well as the Chief Pilot of the Mars Ingenuity rover. So Havar Grip, welcome and thanks for joining me.
Thank you.
So firstly, obviously developing a helicopter to fly on a different planet is just beyond challenging. So what sort of challenges do you encounter when trying to fly on Mars?
Yeah, so there are many different challenges, of course. The one that really stands out about Mars specifically is that the atmosphere is extremely thin compared to Earth. And we are, after all, flying a helicopter, and helicopters need some amount of atmosphere to sort of bite into in order to generate thrust. And we just don't have a whole lot of it on Mars. And so that sort of is one of the things that sort of sets the parameters for everything else on a helicopter. We have to have a large rotor system compared to the rest of the helicopter. We have to spin the rotor fast, and we just have to make everything really lightweight in order to be able to lift it. And then the atmosphere also impacts just how the helicopter behaves when you try to control it. It behaves a little bit differently because of the thin atmosphere than it would on Earth.
Right. So speaking about the spinning the blades faster, what sort of RPM are you looking at trying to just hover, sustain flight?
Are you asking what RPM?
Yeah, what RPM, sorry.
Between about 24 to 2,500 RPM is what we're spinning at.
And is that just to increase the mass flow rate going through to, yeah? Yeah,
so basically, you want to try to spin as fast as you can without encountering, speed of sound issues at the tips.
Yeah, right.
And so we're spinning to where, we don't go higher than like 0.6, 0.7 Mach at the tips. And that's actually a little bit slower than you would for the same, Mach number constraint on Earth, because the speed of sound on Mars is a little bit lower than it is on Earth.
To illustrate how much of a challenge this really is, I've drawn a visual relative comparison between the atmospheric density on Earth and Mars. Clearly, in reality, this is not an accurate representation of the actual atmospheric density, as it is much, much greater than what can be displayed on a screen with dots. We can calculate the speed of the propeller tips using a few simple formulas and information about the helicopter, starting with the radius of 0.6 meters. From this, we can calculate the circumference, which is the distance the tip travels in one rotation. The result is 6/5 pi meters. We also know that the propellers will spin at roughly 2,500 RPM. Using this, we can calculate the distance travelled by the tip per minute by multiplying 2,500 by 6/5 pi. This results in a distance travelled of 3,000 pi in 1 minute. To work out the speed in kilometers per hour, we multiply the 3,000 pi by 60, which gives 180,000 pi meters in 1 hour. This results in a speed of approximately 565 kilometers per hour. Finally, to work out the Mach speed, we take the speed of sound on Mars, which is roughly 880 kilometers per hour, and divide 565 by 880. This reveals a speed of roughly Mach 0.64 for the blade tips.
But as you said, yes, the goal is, an helicopter basically moves air through the rotor like a fan, and you have to move enough of it, add enough momentum to that air in order to generate enough thrust.
This is my very simplified version of the Ingenuity helicopter and its airstream. V0 in the top right represents the velocity of the free stream of air, and in this case is equal to 0, as we are not translating upwards, we're just hovering. Vp in the middle represents the speed of the air at the propeller system, and Ve represents the exit velocity of the air from the propellers. The mass flow rate is defined as the mass of air being pushed through the propeller system per unit time. By pushing this air downwards, the helicopter is propelled upwards due to Newton's second law of motion. Mass flow rate is denoted by the symbol m dot, which is equal to rho multiplied by Vp multiplied by A, where rho is the density of the Martian atmosphere, which is 0.02. A is the area of the circle the propellers form, which is pi r squared, or 9/25 pi. And Vp is the velocity of the air at the plane of the propellers, as shown on the diagram. We can work out Vp using the formula of the square root of the thrust over area multiplied by 1/2 rho. We know that the thrust is 6.7 newtons due to the weight of the helicopter, which is just 1.8 kilograms, which is the mass, multiplied by the acceleration due to gravity, which on Mars is 3.71. And that results in a thrust of 6.7 newtons. So putting in substituting in our values, we come to a result which is 12.17 meters per second. So that is the velocity of the air at the propeller system. Using this, we can now calculate the mass flow rate by multiplying 0.02 by 12.17 and 9/25 pi. And this results in an answer of 0.275 kilograms per second. We can check this answer by using the formula Vp equals half Ve plus V0. So writing this out gives 24.34 is equal to Ve plus V0. And as already mentioned, V0 is just equal to 0 in this case when it's just hovering. So Ve is 24.34 meters per second. We can use one last formula, which is thrust is equal to the mass flow rate exiting the propellers multiplied by the exit velocity of the air, subtract the mass flow rate in the free stream multiplied by the velocity of air in the free stream, which is 0. So solving this equation gives thrust as 0.275 multiplied by 24.34, which is 6.7 newtons, confirming the numbers. The required mass flow rate is important to engineers as they must design a propeller system to produce this value. So, spinning the blades at such a high RPM must take considerably more power. So what sort of power requirements are you looking at from the battery?
What kind of power draw?
Yeah.
So it's in the, I believe it's in the 200 to 300 watt range when we're talking about hovering the helicopter. Although I might not, have the number exactly, right in my head, but it's in that order.
Okay.
But we have batteries that we tested to much higher,
right,
parallels than that, so we can momentarily draw, much more power than that if we need to.
Yeah. So basically, for accelerating around and moving, you would use that.
Yes. Right.
Yeah. So you mentioned earlier about reducing the mass. Obviously, that's critical in order for the whole system to work. What sort of measures did you take to reduce the mass enough that you could make this project feasible?
So one of the things you have to do is we have to track, or we had to track, every tiniest little piece of hardware down to the sub-gram level, along this whole route, and just be very stingy about what we would be willing to expend mass on. And one of the things that really is enabling is the fact that we have various commercial off-the-shelf components that have been developed in relative recent times for things like cell phones and drone technology that are very lightweight, and we can take advantage of. These are things that are relatively recent, that wouldn't have been available fairly short time ago.
Yeah. Okay. Interesting. So specifically, why did you go for a contra-rotating propeller system over other options?
So I think I heard you ask about the coaxial rotor system.
Yes.
Yeah. That has mostly to do with accommodation. So obviously, we have to be accommodated on the rover. We have to pack up neatly underneath the belly and then be deployed on the surface. And so when we looked at that early on, we determined that would be the easiest path in order to be able to achieve that, would be with a coaxial
just to fit
system.
the dimensions and everything. Obviously, you're on a pretty tight package getting up there.
Yeah.
And so lastly, you're the chief pilot for this. So what does that role sort of entail? What requirements do you do in terms of flying it?
So, I led the development of the flight control system as we were developing that. And so those are the algorithms that basically fly the helicopter, from takeoff to landing, and navigates, in order for the helicopter to know where it is. And so a lot of what when you talk about piloting it is operating those algorithms, giving the right sequences to do the flights that we want it to do. And then there are other piloting tasks, or classical piloting tasks, if you will, of ensuring that, the hardware is in order to fly, that the weather is suitable for flying, planning a flight with the right waypoints, estimating, how long that will take, and making sure that you have the power necessary or the energy necessary, and so on.
The reason the helicopter must fly using pre-written algorithms is very simple. The distance between Earth and Mars is constantly changing, but whatever figure we use, we will reach the same conclusion. So assume the distance at the time of the flight between the two planets is 200 million kilometers, or 2 times 10 to the 11 meters. And given the speed of light is approximately 3 times 10 to the 8 meters per second, we can work out how long it would take a signal to get to Mars by dividing the distance by the speed. This gives a time of approximately 11 minutes for our signal to reach Mars. Considering piloting is usually a feedback loop, we reach a two-way communication time of greater than 20 minutes. This is obviously very impractical, so the helicopter must fly autonomously. So Havard's job was to construct the algorithms that give Ingenuity the ability to fly itself, and Havard and his team must oversee and choose when flight is appropriate based on many factors, including weather and the battery status. I've come to realise that the real challenge for designing this helicopter was the integration of many different parts coming together to work as one. We have batteries, we know how to make propellers, we have ample knowledge in solar power, but in such a delicate system, altering one feature of one part has an effect on almost every other part in that system. I've drawn this diagram which should help to illustrate the difficulty in assembling a functioning helicopter, especially for a different planet. If we alter the blade diameter, we change the mass. If the mass is changed, we need to alter the battery size. If we alter the blade speed, we need to alter the diameter to ensure the tips are travelling at an acceptable speed. The blade speed also adjusts our power requirements, which means either using a larger battery, which will increase mass, or compromising flight time. And all of this must fit into a certain spot on Perseverance. This is just a testament to how hardworking and skilled the engineers at NASA and JPL are. And speaking of NASA and JPL, a huge thanks to Havard and the rest of the NASA team who made our interview and this video possible.